Okay, so welcome back. Today we'll do, so we still have a couple things to finish with the dot product. I just want to do a couple more examples. Um, and then we will move on to the cross product, and then that will basically be all the quantities we need to be able to define the geometric things we care about. So the point of chapter 11 really is putting the foundation in place so that we can talk about lines and planes in space. So that's really the goal of what we're doing in chapter 11. That's the last two sections of chapter 11 is dealing with lines and planes in space. So anyway, so the way that this goes is the following. Well, maybe before, like I said, I move on, I want to do a couple more examples of the dot product. So last time we saw, if I have the following question, right, how can I tell whether or not, oh, there's no H there, whether or not a given pair of vectors. So how can I tell whether or not a given pair of vectors are orthogonal, are perpendicular? So the word perpendicular, of course, you're used to from high school geometry, so you know what that means. But in 3 dimensions, a lot of times you'll hear the word orthogonal, which is really it's the same thing. But one reason why you might hear that over perpendicular is that perpendicular, it's obvious what that means in a plane. If you're talking about orthogonality, since it's in space, maybe you're like, wait, how could they be perpendicular in the same way? Well, the idea is that if they're in general position, then they occupy some plane, and so they're perpendicular in the normal way in that plane. So really, it means the exact same thing. It's just a different word, so I will use them interchangeably. So the answer, as we saw from last time, is that two vectors A and B are perpendicular if and only if their dot product is 0. So A and B are perpendicular or orthogonal if and only if, so this arrow means the implication goes both ways, if and only if their dot product is 0. Okay. And so this means that the dot product is really, really nice for it's really, really nice for telling immediately whether or not two given vectors are perpendicular, because you just dot them, okay? And dotting two vectors is easy. So quick example. Let's see here. So are the two vectors A. So we'll say A is minus 4I plus 5J plus 7K, and B, written in the same notation, is I minus 2J plus 2K. Are these two vectors perpendicular? Okay, so the answer, of course, is found by dotting them, so let's dot them. So if I dot A and B, what's the result? This is minus 4 times 1 plus 5 times minus 2, right, plus 7 times 2. So this is minus 4 minus 10 plus 14. So this dot product is equal to 0. So the answer is yes. These two vectors are in fact perpendicular. Okay. If you are careful, of course, plotting these things in space, then you would be able to see this. But of course, drawing something in space it's hard to keep it neat and have it look nice. So so this is a nice algebraic way of telling us we don't even have to draw a picture or anything. We can just compute dot product, and this tells us immediately that those two things are perpendicular. Okay, and the contrapositive here is if I dot two vectors together and I get anything other than 0, well, then those vectors are not perpendicular, right? So it's a completely binary thing here. I dot two vectors together. If I get 0, they're perpendicular. If I don't get 0, then they're not perpendicular, right? And it's as simple as that. Okay, one more application of the dot product. This doesn't come up that frequently in this course. This is actually something that you will do. This is something you'll do in Math 240 or 461 if you take it. And this is the notion of projection. So one more application. Of the dot product. Of course, we saw last time that the dot product allows you to compute the angle between two vectors, so that's nice. Okay, so the notion of projection. What is that's going on here? Maybe I want my lines to be somewhat nice. The idea is to project a vector onto another vector. What do I mean by that? So consider this simple picture. Okay, so let's say I have two vectors. Here's a common vertex. We can call that the origin, or we can just say that they share a common initial point. So let's have vectors A and vector B here. Okay, so vector B is this entire vector here. You'll see why I'm making that distinction. And imagine that we had a light source up here. Okay, so we have a light source shining straight down in this direction. Okay, so our light source is shining straight down in this direction. Okay, well, then you might imagine that this vector A casts a shadow on B. Okay, so it casts a shadow on B. So if I imagine drawing in this shadow on vector B, it would look something like that. Okay. Now, This is a mystery vector, right? I want to know, what is this mystery vector? What is that? Well, what's something you can say about that? Well, something you can say about it is that, first of all, what is the relationship between this mystery vector and B? What would you say, right, is the relationship between these two? So I'll give you a couple seconds to think about that. So, forget about what, anything else I've said. You have two vectors drawn here, right? Forget about the labeling even, right? So there's two vectors. You have this vector question mark and this vector B. What's the relationship between those two? I have a question. Would it be wrong if I, J, K have had above them instead of the arrow? No, that's fine. If you want to draw that, I know that in physics a lot of times they use the hat notation. That's perfectly fine. The reason I'm using the little arrow over them is because if I were doing this in typeset, like when I'm gonna do this for your like exams or any homework that I type up, it's just gonna be boldface on paper. There's not going to be a hat or an arrow over them. They're just going to be bold. Unfortunately, I can't do boldface with just a pen. It's no good. They're multiples of each other. Exactly. They're parallel. They're scalar multiples of each other. That's right. So these this vector question mark is a scalar multiple of B. We know that. So whatever this thing is, I'm going to call this the projection of A onto B. Okay, so I'm going to call this the projection of A onto B. What does that look like? This is the projection of A onto B. So this is the projection of A onto B. Now, if you're looking, maybe I should relabel these because in your textbook it projects B onto A, so these are swapped. So maybe I should flip these, but I'm gonna keep this notation because it makes sense if you read it like this. So the projection of A onto B is whatever this vector is. So this is this question mark vector. So question mark is the projection of A onto B. We read that as projection of A onto B. Okay. Oh, why did I put parentheses there? Okay. All right, so what is this? Well, we know automatically that it is some scalar multiple times B, right? But what is that scalar? Well, it is A dot B over the length of B squared. Okay. All right. Now, I'm not going to prove where that scalar comes from. Actually, this is again a triangle. This comes from trig. Does this unknown vector have the same x coordinate as A? Well, yeah. So I mean, okay, if we should be careful here. So the point is that if we have if we've shown this or if we've arranged this picture so that this is the origin, then you can say different things. But this is just a completely general picture here to show you what this projection is. So this is the projection of A onto B, and it looks like that. Projecting a vector onto another vector yields a scalar multiple times that vector. Okay. All right. So, quick example of this. Just one quick thing here. Let's maybe I'll just do it on the same since I already have this written here. So let say U be the vector say 3 minus 1 minus 2, and let V be the vector 2 minus 3 1/2. Okay. So then I want to find the projection of, say, V onto U. Okay, so let's find the projection of V onto U. Okay. So what do I have to compute here? Let me give myself some room. Okay. So I need to compute the dot product of U and V. So what is U dotted with V here? So this is 3 times 2 plus minus 1 times minus 3 plus minus 2 times 1/2. Okay, so this is 6 plus 3 minus 1. All right, so this is 8. Okay. What else do I need to compute here? So I'm projecting I'm projecting V onto U here. So I have to do U dot V, and then I have to do the length of U squared, right? So what is the length of U squared here? Well, first of all, length of U length of U squared. This is just U dotted with itself. Right? Okay. And so this is 3 squared plus minus 1 squared plus minus 2 squared. So this is 9 plus 1 plus 4. So that's 14. Okay. And so the projection of V onto U is U dot V over the length of U squared, that scalar, times U, right? And so this is 8/14 times U. So simplifying this is 4/7 times U. But U is just this vector. Scalar multiplying a vector, I get 4/7 times U, so I get the vector, say, 12/7 minus 4/7 minus 8/7. Okay. Note, I intentionally used this notation instead of IJK notation just to switch it up. Okay. Okay. If you project B onto A, is that the same as moving the light source? You could think of it like that. And of course, this projection, you might say, oh wait, isn't B too long to project onto A? No, because as it turns out, you're not really projecting onto the vector. You're projecting onto the line determined by the vector. So, and even more, in fancier language, you're projecting onto the one-dimensional subspace spanned by the vector. Okay, so you can always do that and make sense of it geometrically, so long as it's not the zero vector, right? So so long as one of your vectors is not the zero vector, then you can make sense of this geometrically. Okay. Again, this doesn't come up that frequently in this course. This is the simplest example of what's called orthogonal projection. This is something that is very, very important in the last bit of Math 240 or Math 461. Okay, and so that is more or less all I wanted to say about the dot product right now. It will be popping up throughout the course. So I want to move on to the cross product. So the cross product of two vectors. Now, as we saw, the dot product of two vectors was a little, it had some properties that were not that ideal, right? So one, it wasn't really closed in the sense that you started with two vectors and you dotted them and you got a scalar. Okay. So with the cross product, it's going to be different, right? It is going to be an actual closed product in the sense that you start with two vectors, you cross them, and you get a third vector. Okay. So the bad thing about the cross product is that it's hard to compute. Okay, so the good. Okay, so cross product of two vectors we will write like this. And we will read that A cross B. So the good is that the cross product of two vectors is a vector. Okay, that's the first good thing. The second good thing that we'll see, I'll be vague right now, but the cross product has nice geometric properties. Okay, so of course the dot product had really, really nice geometric properties, which is why it was studied as a product. The cross product, similarly, is a fine notion of a product because it has nice geometric properties. The bad is that it is nastier to compute than the dot product. So while the dot product is really, really straightforward and simple to compute, the cross product is actually a little nasty and it's something that you can't, the dot product is something that basically after you've practiced a little bit, you can look at two vectors and do the dot product in your head, basically, if the numbers aren't too bad. For the cross product, you can't quite do that. It's a little more annoying. And then it has algebraic properties that are not as nice. As the dot product. Okay, and you'll see exactly what I mean by this. Okay. So, before I can define this, I have to do a little aside here and talk about determinants of matrices. So I need to first talk about determinants. Okay. So I'm not going to give you the full rundown of determinants of matrices. That is the contents of Chapter 3 in the Math 240 textbook. So maybe you've had experience with this before, maybe not. It doesn't matter. What I'm going to do here is entirely self-contained for what we need. Let's first of all start with what is a matrix. So the simplest matrix would be a 1-by-1 matrix. To talk about determinants, the matrix in question has to be square, which just means that it has the same number of rows and columns. So a 1-by-1 matrix is just a number. So a 1-by-1 matrix A, that's just a real number A. So real number is an example of a very stupid sort of matrix. A 2-by-2 matrix looks like this. So this is a 2-by-2 matrix. A, B, and C. A, B, C, and D are real numbers. Okay, and a 3-by-3 matrix looks like this. So this is a 3-by-3 matrix. I'm not going to write all that, but all those are real numbers. Oh, sorry. Okay, so those are matrices. Now, you might question, like, what is a matrix? So here it's just like a block of real numbers. What's the proper way of thinking about this? A matrix is a vector of vectors, right? So a matrix is a vector of vectors. Okay, that's really what's going on. Okay, what do I mean by that? I mean, a 3-by-3 matrix is really a vector that has 3 components, where each component is a vector with 3 entries. Right. So imagine there's 3 slots here, 1, 2, 3, and in those 3 slots we have 3 vectors. You might say, wait, where does the vectors come in? That's not one of our notations for vectors. One quick thing I will say. So note, a basic example of a matrix is a vector. Okay. Note, a matrix that looks like this. So let's write it like A1, A2, A3. So this is a matrix that has 3 rows and 1 column. Okay. This is a vector. What kind of vector is it? Well, this is the same as the vector A1, A2, A3, or the vector A1I plus A2J plus A3K. So just like for a vector, we had this way of writing it, and we had this way of writing it, but they were the same vector. This is just another way of writing it, okay? This is called writing it as a column vector, but a column vector is a vector. So all these 3 things are equivalent ways of writing the same vector. Now, in order to actually be rigorous with all of that, I would have to go further into something called isomorphism of vector spaces. I'm not going to do that. So just take my word for it that these 3 things are exactly the same, and there's absolutely no difference between any of the computations you do, whether you're using any of these 3 notations. So you've already had experience with matrices, even if you've never seen them before in another course, just because any vector is actually a matrix. Okay, it's a 3 by 1 matrix if it's a vector in R3. Okay. Yeah, of course. So the question was, is it possible to visualize a 3 by 3 matrix if each entry is a vector? Yeah. So the I mean, basically, think about exactly how you would visualize R3, and then think about the points that you would plot, right? Each entry would itself be a vector. Now, the problem is that if you have full freedom in each slot, this would be a 9-dimensional thing, right? So can you visualize it in terms of, can you visualize 9 spatial dimensions? No. But of course, can you like draw points and say, this is a point that I'm drawing here, but it's actually a vector? Yes. I mean, maybe that's not too satisfying, but anyway. So a matrix that looks like this is a vector. So you have some experience with these, like I said, whether you know it or not. Now, I've talked about determinants. So a determinant of a 1 by 1 is nothing. So just forget about it. So then we talk about the determinant of a 2 by 2 matrix is defined as the following. So sometimes you write determinant of 2 by 2 matrix like this. Other times so an equivalent way of writing this is using the like absolute value signs, putting the matrix like this. This is just a shorthand version. Okay, but what does this mean? What this is A times D minus B times C. That is the determinant of a 2 by 2 matrix. Now, my goal right now is not to get into a discussion of why the determinant does what it does or what is the point of a determinant. A determinant is extremely important. It is the thing that tells you whether or not a matrix has an inverse. Now, I'm not going to get into matrix inverses or anything because we're not going to use that in this class. All we need to do is be able to write out a determinant of 2 by 2s and 3 by 3s. Okay, and actually we're going to cheat and we're not really going to do a full determinant of a 3 by 3. So you'll see what I mean here in a second. Okay, so here's the determinant of a 2 by 2 matrix. So quick example. Let's compute the determinant of the matrix minus 1, 3, 5, 7. Okay, so what is this? This is minus 1 times 7 minus 3 times 5. So this is minus 7 minus 15. So this is minus 22. So the determinant of this 2 by 2 matrix minus 1, 3, 5, 7 is minus 22. What does the determinant mean? If it's 0, the matrix has an inverse, and if it's not 0, it doesn't. Okay, you don't have to worry about that though for this course, but that's what the determinant means. Okay, now we need to define the determinant of a 3 by 3. The determinant formula for larger and larger matrices can be defined recursively in terms of determinants of smaller matrices. So the determinant of a 3 by 3 can be determined as a bunch of determinants of 2 by 2s. The determinant of a 4 by 4 can be determined as a bunch of determinants of 3 by 3s, and so on. This method of doing it is called, this is just the definition of the determinant. So we're not going to do anything fancy with this. So then if I have a matrix, so I'm going to write it as determinant of the matrix as follows. I'm going to write this. This is not typical notation if you're doing this in Math 240, but I'm going to keep it simple and write this as the determinant of matrix ABC, DEF, GHI. These are all real numbers. Okay. How do I compute the determinant of this thing? Well, the determinant of this thing is, there's a formula for this called the cofactor expansion formula. We're not going to do that. We're going to do what's called expansion across the first row. What that means is that I start out with the first entry here in the first row, A. Okay, that's a number, and I take that number A, and what I do is I take my pen, okay, and I say, okay, A is in the first row and the first column. So I take my pen and I cover up the column that A is in, okay, and I also cover up the row that A is in. And when I do that in this matrix, what I'm left with is a 2 by 2 matrix EFHI. Okay, this is called this is called a cofactor matrix. You don't have to remember that. The way that I determine this, however, is I look at that first entry and I cover up the column that it's in and the row that it's in. Now, we're always going to be covering up the first row, okay? There's other ways to compute the determinant. Don't worry about that. We're always going to be covering up the first row, okay? So it's the column that we cover up that changes. So in this case, we've covered up first row, first column. And so what we're left with is the 2 by 2 matrix EFHI. So then A is multiplied by, oh, I need another black pen. A is multiplied by the determinant of that matrix that's left, EFHI. Okay. All right. Now next, this is very important, okay. Next is a minus sign. This minus sign is always here, okay. What I mean by always here is the operation you do here is always subtraction. It could be that this thing that comes next is a negative number, in which case this would be minus a minus, and so it would become a plus. So I don't mean that it's always literally a minus in that sense, but this operation is always minus. Okay, this is the definition of the determinant. The determinant is this thing called an alternating sum, okay, and so it means that we have plus minus plus. Okay, is the way that this goes. Okay, so this is always a minus. So then what I do next is I take the next entry in the first row, B, okay, and I multiply that by the determinant of a 2 by 2 that I get from this same process. So I cover up the first row like I did before, and I cover up the column that B is in, which is the second column. So I cover up first row and second column. So what matrix am I left with? The 2 by 2 matrix DFGI. Okay. Okay, lastly, I add, so this is C times the determinant of a 2 by 2 matrix that I obtain in the exact same way. So I cover up the top row as always, and I cover up the column that that C is in, which is the third column, and I'm left with a 2 by 2 matrix DEGH. Okay. All right. This is the way to remember how this is computed. Okay. And so what do I do here? So here I now go about expanding this. I compute these determinants. So these are all determinants of 2 by 2s. So this would be A times E times I minus F times H minus B times D times I minus F times G plus C times D times H minus E times G. This is my determinant of a 3 by 3. Now, should you remember this? Absolutely not. Right? This is not the thing to memorize. Similarly, in the textbook, there is a component-wise definition of determinant that has a bunch of subscripts. Okay, or sorry, not determinant, but the cross product. There's a component-wise description of the cross product in terms, complete generality, in terms of a bunch of subscripts of components. Should you memorize that? No. You should remember the process. That is much easier to do than actually remembering where all the indices go. Okay, and so how does this relate to the cross product? So now, let's see how we use this to define the cross product. Okay, so let A be the vector A1, A2, A3. And let B be the vector B1, B2, B3. Okay. All right. Exactly. So someone just said it in chat. So we cheat here. We cheat because we pretend like the top row here are the letters I, J, and K representing these basis vectors, I, J, and K. So here's where I, J, and K notation is very helpful. Now, is it necessary? Like, could we do all of Calc 3 without ever using the I, J, K notation? Of course. Okay, but it would require you to remember a component definition of the cross product, which of course is possible. You can do that. But in terms of kind of doing it on the fly or understanding what's happening, it's just easier to do it this way for notation's sake. So let A and B be these vectors here. Then how do I define A cross B? Okay. This is defined to be the determinant, okay, of a 3 by 3 matrix. And the 3 by 3 matrix in question, its top row is IJK, those vectors. Now, you might complain. You might say, wait, up here, A, B, and C were real numbers, but here I, J, and K are vectors. So how are you allowed to do this? We are pretending that I, J, and K are numbers because we're just going to treat them purely formally. Okay, they're just letters, and we're going to manipulate them using algebra as if they were these numbers A, B, and C here. Okay, so you'll see how this goes. And then in the middle row, I put A. So A1, A2, A3. Those three numbers coming from A go here. All right, the three numbers coming from B go in the bottom row. Now, it matters. The order matters because, as you'll see, this product is not commutative typically. Okay, so A cross B and B cross A are typically not the same thing. So this matters which vector gets slotted in where. Okay. All right. And so this is how we compute it. We follow the exact same process. So what do I mean when I say this? So just following this, this would be it would be I times the determinant of this matrix here. So I'm going to write it like this. So this would be, so again, since it's I, I'm covering the first column and the first row, and the matrix that's left over is A2, A3, B2, B3. So this is A2, A3, B2, B3. I'm taking the determinant of that, and that's multiplied by I, minus the determinant of something, multiplied by J. What's that something? So again, I'm blocking out the middle column and the top row. So this is A1, A3, B1, B3. And then lastly, plus the determinant of something times k, where that something is, I'm blocking out the top row, and the last column, a1, a2, b1, b2. Right? Now, could you just remember this and not remember this form? Of course, but it's easier to remember it this way. Okay, and then I'm not going to write this out in generality, but this is how you do it. So I'll do some examples, right, to show how this works. Okay, so let's maybe do an example of this right now. All right, and so just going to randomly make up some vectors. So let say A be the vector -1, 0, 5. Let B be the vector 2, 2, 4. Okay, so let's compute A cross B. What is A cross B? So A cross B is the determinant of this weird thing where I, J, and K are my first row. The components of A are my second row, -1, 0, and 5. And the components of B are my third row, so 2, 2, 4. Okay, I'm taking the determinant of that. Now, what does this lead to? So this would be, I'm covering first column, first row. So this is the determinant of the 2 by 2 submatrix 0, 5, 2, 4 times I minus the determinant of, again, covering top row and middle column now. So this is -1, 5, 2, 4. So this is times the vector j plus the 2 by 2 determinant of something times k. I'm covering first row, last column. So this is -1, 0, 2, 2. Okay, so let's see how this goes. What's this determinant? So this is 0 times 4 minus 5 times 2 times I minus -1 times 4 minus 5 times 2 times j plus -1 times 2 minus 0 times 2 times k. Okay, so let's simplify this. So this would be 0 minus 10, so that's minus 10i. All right, minus, here I get -4 minus 10 times j, plus I have -2 minus 0, so this is -2 times k, and so this is the vector minus 10i minus 14, so that's plus 14j minus 2k. Okay. Jack, I mean, you should use something like this. Like, you know, your method for computing the cross product should be this. It should involve a determinant. So, I mean, there are some computational tricks for doing 3 by 3 determinants. So, I mean, if you use that instead, that's fine. But you're still doing a 3 by 3 determinant. So, you should find this by using, you know, finding a 3 by 3 determinant regardless of what you're doing. Okay. All right, and so, look, we get a vector, right? We started with two vectors, A and B. We cross them, we get another vector. Okay, let's do B cross A. All right, so what is B cross A? So the difference here is that now we're computing the determinant of this thing, I, J, K. In the middle row is now B, so this is 2, 2, 4. And in the bottom row is A, so which is -1, 0, 5. So let's see how this alters what's going on here. So in each case, the difference is that, so for instance here, instead of having 0, 5, 2, 4, I have 2, 4, 0, 5 times I. And then in the next slot, instead of having -1, 5, 2, 4, I have 2, 4, -1, 5 times j. Plus, again, I would have 2, 2, -1, 0 times k. Now, you can compute this directly, but I'm just going to say, well, it turns out for the determinant, if you are computing the determinant of a matrix and you swap the rows, like if you swap two rows, that flips the sign of the determinant. So each of these is going to be minus what it was up here. And so what we get is that this is 10i. You can just compute that. It's 10 minus 0. Here, this is 10, so this is 10 minus minus 4, so it's 14. So this is minus 14j. And then this is 0 minus minus 2, so that's 2, so plus 2. Okay, notice this is exactly minus what I got up here. And so B cross A is a different vector. It's actually minus A cross B. And that's always true, right? One thing, I'm not going to prove that's always true. You can do that just have two vectors A and B, completely generic, A1, A2, A3, B1, B2, B3. Compute A cross B and B cross A. You can just see that it's always the case. But of course, I just came up with these two numbers, right? I just literally made these up. So of course, the probability that I just made up two numbers that this worked for is pretty low if you think about what goes into the cross product. But you can show this directly. Okay, so of course that's one property. So note, A cross B is equal to minus B cross A. Okay, so one, that's nice to know how these two things are related, but i.e., the cross product is not commutative. So this is one of your earliest examples of a product, a type of multiplication that is not commutative. A times B is not the same as B times A. Okay, now this is an example of something that's like skew commutative because it's predictable, at least. It's not just completely up in the air. But still, this is an example of a product that is not commutative. Okay. All right. So again, someone was asking about the alternating thing. Remember, I said that in the determinant, this sign is always a minus. This always goes plus, minus, plus when we do it like this. And what I mean by always a minus is I always put this minus here. Of course, it could work out that in the actual answer, this is a positive thing. So that's not, I don't mean that this second component is always negative. That's not what I mean. But what I mean is that operation that goes there is always a minus. Okay, which is sometimes going to lead to a second component that's positive, sometimes it's going to lead to a second component that's negative. Okay, but that's just how the determinant is defined. There's nothing, you're not computing anything there. That is the definition of the determinant. Okay, now, what are some other facts, geometric facts about the cross product that make it nice? Okay. Well, as we saw with the dot product, right? Dot product was intimately related to the notion of length. Right? So there was the clear relation between the dot product and the length of a vector. There was a clear relationship between the dot product and angle between two vectors. So it was related to length and angle. And specifically, it told you whether or not two vectors were perpendicular. Okay. So in a similar way, so here's two facts. Okay. So maybe I'll list them as facts here. So the first one is A and B are parallel if and only if A cross B is equal to 0. Now, what is wrong with what I just wrote? All right, so for the dot product, if A dot B is equal to 0, it meant that A and B are perpendicular. Conversely, if A and B are perpendicular, then A dot B is equal to 0. Okay, what is wrong with what I've written here? So what I've written here is almost true, but I wrote something that is nonsense. So what is the part of this that is nonsensical? It's the zero vector, exactly, right? So saying that the A cross B is equal to 0 doesn't make any sense because 0 is a number. Okay, so it's if A cross B is equal to the 0 vector. Okay, that's the statement. So now this is true. Okay, A and B are parallel if and only if A cross B is equal to the 0 vector. Okay, right? Because A cross B is always a vector. It is not a scalar. It's always a vector. Okay, but this means that we can talk about triple products, right? A cross B cross C is something we can talk about because we couldn't do that with dot products, right? So we couldn't talk about A dot B dot C because A dot B was a scalar, and then dotting a scalar by a vector didn't make any sense. But having a triple product of, triple cross product makes sense because the cross product of two vectors is vector, so I can cross two vectors and then cross it with a third vector. So that's something else I can do. Now, note, here is a warning. While this is nice, you should never do this to check if two vectors are parallel. Why? Why should you never do this to check if two vectors are parallel? Okay, even though that this fact is 100% true, this is definitely a fact, why shouldn't I ever use the cross product to check if they're parallel? So the dot product, I see a question in the chat. Dot product doesn't tell me if they're parallel. Right, so dot product doesn't really tell me if they're parallel, but there is something I can do faster to check. Right. Well, what's easier and faster to compute is, what does it mean if two vectors are parallel? It doesn't mean their dot product's 1. Doesn't mean their dot product is whatever. Right? If two vectors are parallel, it just means they're scalar multiples of each other. So I don't have to compute anything. I can just look at them. Right? So why? It's quicker to just check directly. Okay, it's quicker to just look at them because two vectors are parallel, they're going to be scalar multiples of each other. So you can look at the two vectors, right, and just go component by component. So if the first component of 1 is 1 and the component of the next one is 5, the first component, I mean, then the only option would be one would be 5 times the other. So then you just check, is this one 5 times that one? If there's a multiple that doesn't match up, then they're not scalar multiples, then that's it, right? So it's really easy to look at two vectors and see if they're scalar multiples. So checking if two vectors are parallel should be something that you do very quickly. Okay, so don't use the cross product to do that. Okay, now the very, very big thing that I should say, maybe I'll write it on another page because it's so important. Okay, and so here is triple star fact. This is the most important use of the cross product we have in this entire course. Okay, so how are we going to use the cross product in this course? The cross product is going to be used as the easiest way to come up with a third vector that is perpendicular to two given vectors. Okay, so the most important use of the cross product by far in this course is as a way of generating a vector that is perpendicular or orthogonal to two given vectors. Okay, so I'm out of time, so we'll do this at the beginning of class next time. But what does the cross product do? The idea is that if I have two vectors on my paper here, So here's a vector, and here's a vector. And we'll say that this vector is no, I should have, here, I'm going to do it this way. So here's my vector B, and here's my vector A. Okay. Then where is A cross B? A cross B comes right out of the paper. Okay. Oh, I can't see A. I've blocked A entirely. A cross B comes right out of the paper. Okay, like this. So that's A cross B, this pin. And this is via what's called the right-hand rule, which I'll talk about next time, which is if I take the knife edge of my hand here, and of my right hand, and I line that up with my first vector A, and I allow my fingers to curl towards the second vector B, then the direction that my thumb points indicates the direction of A cross B. So there's only two options. It either points out of the page or into the page, right? And so whether I'm doing A cross B or B cross A, right, those are my two directions. So I'll talk about that next time, since I am out of time for today. Okay, so Wednesday we'll finish that up, and then we'll talk about lines in space. So do lines in space and planes in space after that, and then that'll be chapter 11. So then we'll have basically another 2 weeks, and it'll be time for your first exam, because your first exam covers chapters 11 and 12. Chapter 12 we'll cover pretty quick. We'll cover the entirety of chapter 12 in about 3 days, 3.5 days. So anyway, I'll post the exam schedule, or at least I'll tell you when your first exam is going to be soon, like over the next couple days. I haven't finished. I still have some emails I didn't get to, so if you emailed me last week and I didn't respond yet, don't worry about it. I will try to get to you before Wednesday. If I haven't responded by Wednesday, then please let me know. You can send me another email or just forward the old email to remind me. Homework, I will post homework on Wednesday. So yeah, I'll post homework on Wednesday, and it'll be due next Monday or next Wednesday, something like that. Okay, so that's the deal. I'll see you all on Wednesday.